Okay, good day. Let's start our wind loads by this introduction, this topic. So I will just discuss why is it important to know the correct wind loads. No, that is based on NSCP 2015, in which the NSCP 2015 is literally based on ASCE 7, either 7-10. But I will show it this one as ASCE 7-16. So anyway, let's continue. So why is it wind load is important? Because if you don't know the correct loading so that you can design your structure well, then that wind can cause significant failure or in much worse scenario, catastrophic failure. So I will show you some videos about the effect of wind in structure. So first I will show you the most famous bridge, the Tacoma Bridge. No, it collapsed. No, so you can try to watch it. uh,
Bridge, Washington, opened
so
only a
just
few months
try.
ago, was built at a cost of over $6 million. But misfortune overtakes the great structure. These are some of the most amazing pictures ever recorded by a newsreel. The actual collapse of the world's third largest suspension bridge.
So this is phenomenon what we call resonance. The fundamental frequency of the bridge matches the loading frequency of the wind.
Only a 35 mile
And
an
because
hour
of
wind
that,
is
we have
blowing,
a
but this
resonance.
apparently sets up a rhythmic swinging of the bridge, which increases with each swing.
This is the cause of the wind. This is the cause of the wind blowing.
Finally, the swinging road and the suspension cables give way and plunge into the water below. Fortunately, the only casualties were a car stalled on the bridge and a dog.
So this is from the Tacoma Bridge collapse by the British Path channel. You can watch this. Just search for the Tacoma Bridge. And for this next video, this is very graphic. I urge you to watch this because this is a very important scenario in which this is from the Facebook of Bombo Radio Philippines. And this is from the collapse of the Siargao Complex Gymnasium. It served as an evacuation center for the people, but unfortunately, the strong winds of Typhoon Odette. This is Typhoon Odette. Just watch the video. Okay. Sino mo sila magdala ng water? Sila di wala ka. Chat ko sila. So as you can see, there is internal pressure. Both the internal pressure and also the external wind pressure because of the strong winds of Typhoon Odette. You can first see the components and cladding reacting to the wind. And after that, the whole structure, even the main wind force resisting system has collapsed. This is why it is very important to know that wind loads is very important. Yes, because it can cause catastrophic collapse. That is why this is the reason why we have this topic in structural design, especially in steel design. So that's it. You can watch this video in Facebook. Just search for Siargao wind collapse. So anyway, so that is the reason why you see wind load is important. Along with earthquake loading, but that is for the time, for other times, and you can also watch the earthquake engineering videos there on how we can try to solve earthquake loading. Anyway, there is other videos for that, but we focus now on wind loading. Although the ASCE is explicitly said that wind load and earthquake loading are not combined. They don't combine in one case. We cannot see a load case combination in which both wind and earthquake contribute to the overall lateral. Because when earthquake and wind loading simultaneously occur, it is the end of the world. No? So typhoons and earthquake is much more unlikely to happen, but we don't know what will happen in the future. But anyway, let's continue. So this is the reason why I made this video, is to know some of the basic terms. So this is one of the important terms that you need to know. It is the ridge. Ridge is just the highest peak in a roofing. No? As you can see, this is the ridge here in elevation view and ridge in plan view. So no more explanations here. Then this is the most important one, the windward. So as you can see here, as it circles the term windward, that is the side in which it is immediately facing the wind. No, so that is when the wind is blowing from the, let's say, left to right. The windward wall is the immediate wall that faces the wind, and the windward roof is on the side in which it immediately faces the wind. Same with here in this plan view. The wind blows from, let's say, this is north to south, no. So as you can see, the windward wall is immediately facing the wind. So as you can see here, class, we have two distinct scenarios here. The first scenario is this wind is normal to the roof, that is normal to the roof, or perpendicular to the ridge. I mean, sorry, not roof. Perpendicular to the ridge. This is the ridge here. Okay, let's say perpendicular to the ridge, no? So that is first scenario. Then next, the wind is parallel, no? Parallel to the ridge. So anyway, let's continue. So if we have a windward term, there's also a leeward term. That is the side in which the side is sheltered away from the wind. As you can see here, the the leeward side is here. So if the windward, as you can see here in the plan view, so focus here on plan view, only one wall only one wall is the windward wall and else is leeward wall. So mostly leeward side. Later we can see the other terms such as suction and positive pressure. So let's try to continue. So this is what I am saying. Suction is the negative wind pressure. So as you can see, on all walls that is leeward, like earlier, I have defined what is leeward. Leeward walls and roof are mostly in a suction force. So it is a negative wind pressure. It means that it pulls out the elements away from the building. So so suction means pulling the elements away from the building. In contrast to the what we call the positive pressure. So this is the positive pressure. So positive pressure is the side of structure in which is blowing. It is the side of structure or object that is sheltered from the... sorry, I did not. Okay. My definition is wrong. I'm very sorry. I did not. I just copied it. I did not. So this is not. So as you can see here, if you don't bother with this definition. Positive wind pressure is just the opposite of suction. It blows towards the plane or the roof, if you see that. So mostly it is in the windward wall, and sometimes there is a two case, no. In roofing, in roof, mostly roof is in suction, but sometimes the windward roof side experiences positive pressure. That is why later in the code, we have two scenarios or two values for both the windward roof. No, but leeward roof always is in suction. But mostly, most of the time, if the wind is from any part, let's say parallel to the ridge or perpendicular to the ridge, mostly the roof is in suction. So anyway, let's continue. Don't bother with the ano. So internal pressure, this is what we are seeing earlier in the video in the evacuation center. Internal pressure builds up if the structure is enclosed. If the structure is not, what you call that, really tight in air, like for example, most buildings like airplane hangars, and that is why there is an important term we call the enclosure classification. So I will not really bothered on discussing this one. As you can see, it is very easy to understand what are this meaning. So anyway, In this is what I get in ASCE 7-16. We have this new term, partially open buildings, no? In NSCP 2015 and ASCE 7-10 or in 2010 code of ASCE 7, there is no partially open buildings. So there is no partially open buildings. But in 2016 code of ASCE 7, there is now what we call a partially open building. So this is the internal pressure coefficient, no? I will not really bother to discuss this one because this is just straightforward. You can see this is a very straightforward on how to use. I will just show you. Unfortunately, in ETABS, there is no internal pressure coefficient, but watch for my other videos or for future videos that I will show you how can we include internal pressure coefficient in ETABS. Because ETABS has an auto load feature, then we can try using the CPI or the CP or that what we call the vertical the velocity wind coefficients, no. Okay. So this is so much easier. So before that, I would just like to add why is it that ASCE 7-16 or the 2016 or the latest ASCE code included partially open buildings because when the partially enclosed buildings, this is my takeaway, if some of the claddings in a components and cladding perspective, no, in some of the claddings of a enclosed building or partially enclosed buildings have been blown away, then it can go into or it can transform into a partially open buildings. So the loading there will change, but it does not really give us much of the variation here in GCPI. But as you can closely look, the partially enclosed buildings such as hangars, if mostly hangars don't have a door. Hangars are the garage for airplanes, don't have a doors. Then that is mostly a partially enclosed building, as you can see here. This is the definition of partially enclosed building. It gives us a higher internal pressure coefficient. So it is very important to determine if your structure is enclosed or partially enclosed because the internal pressure coefficient are different. And as you can see, the internal pressure is very high in partially enclosed buildings. Like for example, in an evacuation center, if we design it using this one, internal pressure coefficient of 0.18, not knowing that it is not really enclosed but it is partially enclosed, then there is wrong loading there because the true internal pressure coefficient is this one. So you cannot also assume that it is always internal pressure coefficient for this one because it will give you a very overload. You will have an overloading of wind. So anyway, this is what I'm talking about, that in NSCP 2015, the provision can be seen in 207A, but unfortunately, partially open classification was just introduced in 2016. So NSCP 2015 is a year before that 2016. That is why there is no partially open buildings na provision or definition there. So anyway, let's continue. Some notations. This is important class, the mean roof height, the height above ground, the angle of plane of roof from horizontal. So what are these? So I will just show you. Okay, I forgot. No? I will just show you this one. I will show you this picture. As you can see, the mean roof height is just the average between the ridge height and the eave height. So it's very easy. And theta is the angle of plane of roof from horizontal. So this is very straightforward notations. And as you can see, Z here, I did not really bother to extend this one because Z is, as you can see, if you apply this in windward wall, the Z here or height above the ground is varying. And thus, the pressure or the design pressure of our windward wall, no, uh, is varying. So later I will show you that, no. And as you can see in both roof, in the windward roof and the leeward roof, so in the windward roof and the leeward roof and the windward wall, they use it. We will use H. We will use the H mean roof height. But for this one, for this windward wall, we will use the height above ground, that is it changes, no, it has ano, what you call that, variation. So next, our horizontal dimension of building measured normal to the wind direction and horizontal. So as you can see, if our wind is normal to the ridge, this is perpendicular to the ridge, perpendicular to the ridge. Our B here is normal. So our B here is perpendicular to the wind. So this is wind, this is perpendicular, and our horizontal dimension is this one. So similarly, if it is parallel, then our B will change. This is our B, this is our L. So this is the meaning of some letters here. Don't forget this because this is very important in determining CP. So CP has other videos. CP. This is what we call the velocity coefficient. No? Okay. So design pressure P. So this is very important also. Q, QI, G, gas effect factor, you can find it in their video. I have a very nice lecture about gas effect factor. You can see it. There is an example computation. And just watch on how we get the G. The CP or the pressure coefficients, I also have some videos about pressure coefficients. Watch it. The GCPI is here is in the enclosure classification. This is the GCPI. This is the GCPI. So important GCPI. So I will not discuss it because this is very straightforward. Just use that. But I will show you. Okay. Uh, then then the velocity pressure Q. So this is what I'm saying. We have the velocity pressure Q in terms of height Z. So you know the meaning of Z. And in terms of the mean roof height H. So this one is used for the roof and leeward wall. Leeward wall. So this is for the windward wall. So WW. So we called it the windward wall, the QZ. So anyway, as you can see here, it varies. Don't forget that it varies for the windward wall, QH, mean roof height, KZ. This is the term that is varying, the KZ and KH, which is the same, but it is different because the H or the Z we use is the mean roof height for H, and for Z this is the varying one. So we will discuss it here. KZT, sorry, KZT, the topographic factor, just watch my video about this. I have an interesting example for KZT. I use the Google Earth for determining the profile elevation or the profile of the topography because topography has very important effect on wind loading. Then wind directionality factor, we will discuss it here. It will have its own slide, and the ground elevation factor. So the basic wind speed before we go, this is important. It so happened that some of the websites have velocity basic wind speed. So you just go to global.com, global.com, then just click for your what do you call that, location. Let's say in our school, the University of Southern Mindanao, just click here. Then we can have our basic wind velocity as 80.6 meters per second. So that is 290 kilometers per hour. But if you are if you will create it here, although it's still USM, but in this part it will become 300 kph or 83.3 meters per second. So anyway, let's go back to here. So that is basic wind speed. Just go to the website global.com. Just find it in the internet. So I will discuss this coefficient KZ or KH. As you can see, exposure D gives us the highest velocity pressure coefficient KZ. So I have interesting video about this one. Just watch it about different exposure. And like I said, exposure D gives us the highest wind because this is the area in which there is no obstruction of wind. This is an open, and this is exposure. So anyway, As you can see, you can find it in table 26.10-1. This is the different values of KH or KZ. So, windward wall has a varying design pressure. So, like I said, this is what I'm talking about. Okay. This is what I'm talking about. The windward side, because this is how the blowing of the wind is varying. Because you use KZ. QZ. Yes, KZ. KZ, QZ. So, QZ. But for the different sides like windward roof, leeward roof, and leeward wall, they use H. H for these three. For QZ, you use Z. And Z is varying. That's why the symbol, the ano, earlier in the part is this is Z. But the mean roof height is fixed. So mean roof height is just the mean or the average between the eave height and the ridge height. So that's why it's called mean roof height. So ground elevation factor, it's always 1 KE, and there's no anything to discuss this one, but just assume it is always 1. And the wind directionality factor, that is 0.85 for these two, and I have discussed this in videos about what is the difference between these two. And for other structure, use this one. So anyway, that's it. Okay, thank you. And that's the thing. So wait for my video or just watch the video about CP. This is very important, this CP. CP. So let's go back. What is this CP? Okay, before I go, what is this CP? So this is what we call pressure coefficients. This is we're gonna discuss, and this is part of your quiz. This is the most important because if we want to use ETABS, we need to define different CP. And we will have a discussion about it here in other videos. And I think this is it. Thank you very much. So it's important to know the CP. But anyway, these are just the basics of different classification, different introduction. No, this is just an introduction to wind loads. No? So I hope that you have understand well what are the meaning of these words that we need to understand, especially this kind of definitions, terms, and notations. Especially these notations class. Don't forget these notations. These notations also because it's important in wind loading. Because wind loading is very easy compared to earthquake loading, but in inputting it in ETABS, it's much bothersome because there are so many different cases. So what if the wind blows here? What if the wind blows there? So we consider all the cases of wind blowing and different cases of wind loading or patterns because as you can see here, we have the two cases here in the windward roof. There is a suction and there is a positive pressure. So anyway, that's it. Thank you.